In this video, I'm going to talk about PES, or Photoelectron Spectroscopy. This is a big topic for AP. So this is something you really need to know inside and out, the ideas, and be able to use it. It usually appears in some way on every exam. So PES is basically what they use to provide evidence here that these electron shells exist. You might have wondered, how do we know about this 1s, 2s, 2p? Well, this technique can be used here to prove that these shells exist. So a little bit of background here. They direct light onto atoms, and this excites the electrons, and the electrons get ejected. This is known as the photoelectric effect. But the energy that they're using here, the energy that they're applying, can actually be calculated. So what's happening is these electrons are being ejected, but it takes a certain amount of energy. So the main idea here of PES is that electrons that are closer to the nucleus, all right, closer to the nucleus, they're going to be experiencing more attraction to the nucleus. Essentially, they're penetrating the nucleus more. If you remember that idea, we said like the S electrons penetrate the nucleus more. Well, they have a greater attraction for the nucleus. So electrons that have a greater attraction for the nucleus, that penetrate the nucleus more, that are closer to the nucleus, it's going to take more energy to eject them. All right. And more energy to eject them also relates to the fact that there's a greater nuclear charge. So electrons that are closer to the nucleus take more energy to eject them because they're experiencing the full effects of the nuclear charge. So this idea here is huge, and you really need to understand that. Electrons that are closer to the nucleus penetrate the nucleus more, feel the nuclear charge more, takes more energy to eject them. And then on these PES graphs, you can actually see the different subshells by the different peaks, and how high the peaks are will tell you about how many electrons are in those peaks. So definitely understand this background information, and then we're going to use that as we look at these PES graphs. This picture gives you a little bit more of an idea about what's actually happening here. I'm not saying you need to fully understand this picture in depth or anything like that. I'm just trying to give you an idea about how this works. So you can see here, we're applying some form of energy to these atoms, and the electrons are being ejected. So you can see as the electrons are being ejected, they're going this direction, and then they're being analyzed and detected to get information about the energy involved and how many. All right, so this is just giving you an idea about how this works, how we're applying the energy, the electrons are being ejected, and then we're getting information about those electrons. Same deal for this picture. We're applying some form of energy here. The electrons are being ejected, and then they're being analyzed, and we're creating these PES graphs. So this is not something you need to, need to understand fully or totally in depth, but I just want to give you a little background here about what's actually taking place in this process. Here is a PES graph for nitrogen. So they're telling you flat out that this is for nitrogen, but this is a good place to start because it shows you how you use these graphs. So if you look here, typically energy is going to be on the bottom here on your x-axis, and then your y-axis is going to be relating to the number of electrons. That's what we said. The peaks can tell you information about how many electrons are in a particular subshell here. So if you look at this, and you have to be careful about this, I cannot stress this enough, you have to pay attention to your labels here. So we know energy here is on the X, but notice it starts at 100 and goes lower, all right? Depending on the graph, it might start low and get higher. So you have to really pay attention to this. Cannot stress that enough. Look at the labels and pay attention. We said that the closer these electrons are to your nucleus, it's going to take more energy to eject them. So the way this one's arranged, the more energy is on the left side, and the lower energy is as you go to the right. So this peak here took the most amount of energy to eject those electrons. All right, so this is why this peak represents the 1s for the nitrogen. All right, remember, your s electrons are going to penetrate the nucleus more. They are the lower in energy electron here in terms of the energy level. They are closer to the nucleus. They feel the full nuclear charge the most. So it took more energy to eject those electrons. All right. And then notice as you move to the right here, this is slightly less energy. So this would be the 2s peak because it took a little bit less energy to eject those. And then the very, very last peak here would be your 2p peak because if this is nitrogen, those would take the least amount of energy to eject because they would be the furthest from the nucleus. So closer to the nucleus takes more energy to eject those electrons. All right, you got to really make sure you understand that idea. Closer to the nucleus, more energy to eject those electrons. They're penetrating the nucleus more. They're feeling the full effects of the nuclear charge more. And if you notice the peaks here, these two peaks are the same height because they both have 2 electrons in them. For nitrogen, it's 1s2, 2s2. But then notice the 2p has 3 for nitrogen, so that's why this peak is a little bit higher. So you can kind of use these peaks to see how many electrons there are in these particular subshells as well. So that's how you got to use these PES graphs. All right, you got to pay attention to the energy, and you got to remember that more energy to eject means those electrons are closer to the nucleus. And always pay attention to how that energy is labeled on the graph. So this is a pretty good idea about what a PES graph looks like and how you might have to use it. Now, you don't always know the identity of the element, and you might have to use the PES to figure that out. Let's look at this example now. So here's another PES graph, and it asks, what do the peaks A, B, and C represent for neon? So again, this one is nice. It's telling you flat out that we are looking at a PES for neon. So again, pay attention to how your axis is set up here. We know that the energy here is going along the bottom, but pay attention, we're going from 1,000 down to 0. So we're starting with the highest energy on the left. And we already know more energy to eject the electrons means that those electrons are closer to the nucleus. So if this is neon, think about the electron configuration for neon. The electrons that are closer to the nucleus take more energy to eject them. So peak A would be the 1s2 peak for neon. And then as you go to the right, this is taking less energy to eject these. And notice the pretty big difference here in the energy. It makes sense that these 1s2 electrons for neon take a lot more energy because they penetrate the nucleus more. They're feeling the full effect of the nuclear charge. So then peak B takes less energy, the second least energy here, and that would be your 2s2 electrons. And then notice peak C takes the least amount of energy to eject those electrons. So they're even a little bit further out. That would be your 2p6 electrons here for neon. And notice that the peak for C is higher than A and B. A and B both have 2 electrons in them. And if you look at C, it's much higher because you have 6 electrons in that one. So this was another example where they told you what the element was, and you had to use the ideas here behind PES to kind of analyze the graph here. So again, more energy to eject means those electrons are closer to the nucleus. Here is another example of a PES graph. Probably a good idea to pause the video, try to answer these 2 questions, and then rejoin the video and see how you did to see if you're fully understanding this idea here of PES. So pause the video right now. All right, so hopefully you get these answers here. So the first question says, what do each of the peaks represent? So remember here, the more energy it takes to eject the electrons, the closer they are to the nucleus. But if you notice, in this particular PES, we're going from low energy to higher energy. So it's reversed. You always need to pay attention to how the energy is set up here. So that means the peaks on the right okay, took more energy to eject them from the nucleus. So those electrons are closer to the nucleus. So this first peak here would be the 1s2. All right. And then that means as you go to the left, that's taking less energy to eject those electrons. They're getting further from the nucleus. So that makes this peak the 2s2. So now you have a good idea here about the amount of the electrons. You could pretty much gather that each line here is going to be one electron. So you have kind of one electron here, and then your second electron there. So that can give you a little bit of information. So that tells me for the next peak, this would be the 2p, and it's going to be 6. If you count the lines up, you should be 6. So then that means this peak would be your 3s2. And then the last peak here, that's when you're going to be at your 3p, and you have to pay attention to the amount of electrons that are going to be in this peak. So in this one, it only goes up one line. So this is going to be 3p1. All right, so we labeled what all the peaks represent, but now we need to know the identity of this element. So based on the electron configuration that you just wrote out, the element that would end in 3p1 would be aluminum. All right, so you can see how you can use a PES to be able to figure out the identity of the element, but you also have to be able to identify the peaks, maybe explain why. All right, why is the peak on the far right having the most energy to eject? Understanding this idea of the energy taking to eject these electrons, maybe explaining the peaks. So you need to fully understand PES. And there's more practice on my website. You definitely need to try a lot more of these examples and make sure you're really good with this because this is a big AP topic.